All right, so this is our last day of L'Hopital's rule. This is going to be another strategy for finding the limits of indeterminate forms. So we've talked about that L'Hopital's is really going to be used when you have 0 over 0 or infinity over infinity. So we are going to try to make other indeterminate forms look like that. So for example, 1 to infinity, 0 to 0 raised to the power of 0, or infinity raised to the power of 0, all things that are indeterminate. And so we're going to try to use L'Hopital's. However, in order to do that, we need to take logs first, because you can see that these have exponents, each of these three indeterminate forms. And so we want to get that exponent down and then turn it into one of our L'Hopital's forms, which is 0 over 0 or infinity over infinity. So we're going to use, excuse me, the following fact. Let's say that the limit as x approaches a of the natural log of x, of f of x, with some value L. So now let's keep that on the back burner and let's do something on the other side. This is what I want, okay? I hope you can see that e raised to the natural log of f of x would still be f of x, because an exponential with e and the natural log are inverse functions of each other. They would undo each other. So this is me just rewriting f of x. But we defined the limit of the natural log of f of x as capital L. So I can evaluate this limit by just doing e raised to the limit that I find. So in other words, what we're going to do is we're going to take the limit of the natural log of the function, and then we're going to raise e to that limit. So let's see how we're going to do that. Okay, so the first thing I do is I imagine plugging in, quote unquote, infinity. And if I do that, I would get 1 plus 0 raised to the infinity, which is 1 to the infinity, and that is one of our indeterminate forms. So we're going to say, imagine that f of x was equal to this function here. Then I know that the natural log of f of x is x times the natural log of 1 plus 1 over x, because you can bring the exponent down in front. That's a great property of logs. And then if I decided to try to take the limit as x goes to infinity of this, I'd be taking the limit of this. Well, what do? I imagine, quote unquote, plugging in infinity. I would get infinity times the natural log of 1. This is infinity times 0, which is one of the forms we met on the second day of L'Hopital's, which is it's not quite ready for L'Hopital's, but it can be rewritten there if we were able to rewrite it as a quotient. So I'm going to take this exact limit that I had, and I'm going to rewrite it as a quotient. And we use this strategy in the second day. So this is mathematically equivalent to what was above, but now if you plugged in infinity, you would get 0 over 0, which allows us to use L'Hopital's. So I'm going to use L'Hopital's rule. I'm going to get the limit as x goes to infinity of 1 over u times du dx. This is the derivative of 1 over x, all over, and then again the derivative of 1 over x, which is this. Okay, this is the same thing as the limit as x goes to infinity of, well, these are the same, so they cancel out, of 1 over 1 plus 1 over x. Imagine x going to infinity. This would go to 0. This is 1. Now, the key is that is not your answer. That was the limit of the natural log of f of x. We want the limit as x goes to infinity of just f of x. This is required at the end of these problems. I expect to see you rewrite this. This is me seeing that you understand what you just did. So what we just did was, I know I want this. I know that that is mathematically equivalent to this. This 1 represents that, so this is e to the 1, or e. That is the answer to the problem. Okay, let's try another one. If I take the natural log of this, if I plugged in, excuse me, you should always try to substitute. If I try to substitute, I would get 0 to the 0 power. Indeterminate, but not ready for L'Hopital's. So I'm going to take the natural log of what I'm going to call f of x. I'm just going to define it for clarity for you guys. If I let f of x equal x to the x, and then I take the natural log of that, I'm going to get this. And then I want to write it as a quotient, because if I took the limit as x goes to 0 from the right of x natural log of x, I would be getting 0 times negative infinity. And that's an indeterminate form, but not ready for L'Hopital. So again, I have to write this as a quotient. So I still have not applied L'Hopital's rule. I'm going to rewrite it. Usually the polynomial is the easiest one to write in the denominator. And if I plugged in 0 here, I would be getting negative infinity over infinity, which is ready for L'Hopital. So now I'm going to use L'Hopital rule. And I'm going to take the limit as x goes to 0 from the right side of 1 over x, negative 1 over x squared. Again, simplify this algebra before you try to evaluate. You should always simplify first. If I keep change flip, multiply this up here, I'm taking the limit of this as of negative x, and that is going to be equal to 0. Again, that is not your answer. I expect to see the following. I want this. That is mathematically equivalent to this. This represents the limit of that exponent, therefore this is e to the 0, which is 1. That is the answer to the limit that you found. Okay? We'll try one more. Okay? Again, if you plugged in infinity here, you would be getting, if you plugged in infinity here, you would have infinity raised to the 0, indeterminate form, but not ready for L'Hopital. I'm going to let f of x equal x to the 1 over x. I want to take the natural log so I can get that exponent down. And this is the same thing as this. Now, it looks like I might be in good shape because I already had this written now as a quotient, which, remember, I hope you're starting to see the pattern is what we're going to be wanting to do. So this is the thing that I want to take the limit of. If I imagine plugging in infinity, this would be infinity over infinity, which is ready for L'Hopital. So I use L'Hopital rule. I take the limit as x goes to infinity, and now I take the derivative of the numerator, derivative of the denominator. This is the same thing as the limit as x goes to infinity of 1 over x, which we know is 0. Again, last step, you always have to sort of synthesize what you just did. I want this. This is mathematically equivalent to this. This is the limit you just found. So this is e to the 0, which is 1.